Okay, all right. So I hope all of you are doing well for the GATE preparation and let us begin this today's session. This is session number 9 and today's topic is delta by transformation or delta star transformation, balance three phase systems and per phase analysis. So briefly we will go through the concepts of balance three phase systems and per phase analysis. So what do you mean by balanced three-phase system? A balanced three-phase system has three voltage sources with equal magnitudes but with an angle shift of 120 degree and have equal loads on each phase and have equal impedance on the lines connecting the generators to the loads. So if all these having satisfies all these things, then it is called as balanced three-phase system. Generally, what happens is that all power systems are usually three-phase system and single phase system is used primarily only low voltage low power rating such as residential and some commercial applications. Now if we see the model of balanced three phase system, we can see that the source having three phase voltage having magnitude equal and all are phase displaced by 120 degree. Therefore, we can write it as VAN is equal to V at the angle of 0 degree, VVN will be V at the angle of minus 120 degree, and VCN will be V at the angle of 120 degree, and all are phase displaced by 120 degree. These are phase voltages. Now, these are connected to a balance load having equal per phase impedance, that is Z. So this is the balanced three phase system. Now if you want to if you want to know this neutral current, how you will find? You can find using this KCL. If you apply KCL at the node N, then you will get this node current, neutral current. So neutral current will be the summation of IA, IB and IC, that is these are line currents. Neutral current will be the summation of line currents IA plus IB plus IC. Therefore you can write line current is equal to line current IA will be VN divided by Z and line current IB will be VVN divided by Z and line current IC will be VCN divided by Z. Now on simplifying these values and putting the value of VN, VVN and VCN, so you will get you will get 0 because these are having equal magnitude and are all displaced by the 120 degree. Therefore, we can see that no neutral current in balanced three-phase system. And similarly, you can also tell that uh, this voltage VNN, that is the voltage difference of neutral point, will be also zero. Either this wire is present or not. You can say that voltage difference between the neutral points of source and load will always zero for a balanced three-phase system. Here this is connected, so this is called a three-phase four-wire system. And suppose if this neutral wire is not connected to each other, then it is called three-phase three-wire system. And for a balanced three-phase system, either this wire is present or not, always this voltage difference, that is voltage difference between the neutral points, will be zero. Now if we see this apparent power, three-phase apparent power will be this is equal to the summation of all the phase apparent powers. Like for phase A, we can write VAN IA star plus VVN IB star plus VCN IC star. On summing of all these values, you will get equivalent three phase apparent power as 3 VN IA star. And in all these terms, you can see that here I have noted this voltage and currents by bar. So bar represents the phasor quantities. Now let us see the what are the advantages of three phase power. At any point, if you have any doubt, then you can ask. So what are the advantages of three-phase power? So there are many advantages, like it can transmit more power for same amount of wire, approximately twice as much as single phase. As we all know that for single phase power we require only two wires, and for three phase we require three or four wires. And we can see that in three phase it is three times of the in three phase power is three times of the single phase. In that way you can say that it is transmitting more power for same amount of wire, approx twice as much as single phase. And torque produced by three phase machines is constant. And other advantages for three phase machines are like it uses less material for same power rating, and it starts more easily than the single phase machine. So these are advantages of three phase power. And if you see the three phase system connection, either they are connected in a star connection or delta connection. We call a star connection or bi connection. Now we will see the configuration of a star connection system, balanced star connected system. So we are having three phase sources, VAN, VVN, VCN, and they are connected in a star, and these are line currents IA, IB, IC. So first we assume that phase voltage will be VN is equal to V at the angle of 0 volt, VVN will be at the V same magnitude but they are displaced by 120 degree, and we have assumed the phase sequence ABC, so VVN will be lagging the VN by 120 degree and VCN will be leading the VN by 120 degree. Now we will make the phasor diagram for this star connection system. So let us first make the phase voltages that we have assumed for balanced system. So Vn is V at the angle of 0. So it is here it is represented like Vn will be this and Vcn will be this. Now representing the line voltage on this phasor diagram, we have to find this VAB, that is line voltage. How you can find the line voltage? Line voltage is the difference of the phase voltage VN and VVN. And we have assumed the VN and VVN. On putting these values, you will get root 3 times of phase voltage, and they are leading by 30 degree. Similarly, since the phase voltage are balanced, so line to line voltage are also balanced. Therefore, VVC and VCA will be displaced by 120 degree, and VVC will be lagging in nature, and VCA will be leading by 120 degree with respect to VAB. So we got line to line voltages. So we got line to line voltage, and we know the relation with the phase voltages. So we represent VAB here, and you can also if you want to draw in the phasor diagram, you can also make it like this: VAN minus VVN will be VAB, that is summation of two phasors, and similarly VBC will be ahead of VVN by 30 degree, and VCA will be ahead of leading by VCN by 30 degree. So this is for star connections. Now if you want to find the three phase apparent power, you will get three V phase I phase star. V phase is VAN and IA star. You can take any phase quantity here. Therefore, in summary, if you want to write the for a star connection, you can write like that: line voltage is root 3 times of phase voltage and leading by 30 degree, and line current is equal to phase current. We can see in this a star connection. So this is important point for a star connection, a star connected system. Now let us see for delta connected system. So here we have assumed three per phase impedance Z. They are connected in delta. So here we can see that this phase line voltage and phase voltage equal to line voltage. In delta connection, phase voltage equal to line voltage. So here these phase currents and line currents are different in delta connection. Therefore, first we assume the phase currents like IAB is equal to I at the angle of 0 degree, IBC will be I at the angle of minus 120 degree, ICA will be I at the angle of 120 degree. So first we make the phasor diagram. So first we make the phase currents IAB, IBC, ICA. And now for finding the line currents, that is the current flowing in the line IA, IB, IC, we will use the KCL. So IA will be, you can apply KCL here. You can see that IA, IC are coming to this node and IAB is leaving the node. Therefore, IA will be IAB minus ICA. On simplifying this, you will get root 3 times IA at the angle of minus 30 degree. Similarly, IB will be IBC minus IAB and IC will be ICA minus IBC. So you will get the line currents. And we can see that line currents are root 3 times of phase currents and they are lagging by 30 degree with respect to phase currents. And since the phase currents are balanced, therefore line to line currents are also balanced, and using these values we can represent in the phasor diagram. So if you want to write the summary for delta connection we can write that line voltage equal to phase voltage, and the line current is root 3 times of phase current, and it is lagging by 30 degree. Now if we are having given with a balanced system, a balanced three phase systems, but if you want to make the simpler analysis, then you have to approach like this. Whenever the delta connected loads are given, you should replace with star connected loads with Z star is equal to Z delta divided by 3. This is very important. And you can replace the delta connected source with the star connected source with V phase equal to V line divided by root 3 at the angle of 30 degree. These two approach, these two things you have to put in the balanced three phase system. If suppose if there is already simplified in a star connected system, there is no need to convert into a star connected system. You can simply approach that. But there, if there is a delta connected load or delta connected source are present in the balanced three phase system, first you need to convert in a star connected system. And a delta connected load can be replaced with a star connected load with using this expression Z star is equal to Z delta divided by 3. That is, impedance in a star connection will be one third of the impedance in delta connection. And delta connected sources can be replaced by star connected source with phase value as V line divided by root 3 at the angle of 30 degree. Now we will solve some problems. So first problem is that three equal impedances are connected in delta across a balanced supply. If the same impedances are connected in a star across the same supply, what are the correct options? So this is multiple select question. There may be multiple answers for this problem. Multiple select question. More than one choice can be correct. So whoever is getting the answer, type your answer in chat box, or if you want to speak, then you can tell. So the first case is that we can assume the case 1 and case 2. So you have to compare the case 2 with case 1. So first case is that three equal impedances are connected in delta across a balanced supply. So we have balanced supply, and for simplification we can assume the resistive load. So take the load as R, and this is VA, VV and VC. VAN, VVN, VCN. This is the line current IA, IB, and this is IC. And phase current will be similarly, you can write ABC. Phase current will be IAB, IBC, and ICA. And the case 2 is same the balance system as it is, but with the star connection, with the star connected load. So it will be, so these are R, resistance R, A, B, C, and VAN, VVN, and VCN, and these are line currents IA, IB, and IC. So you have to find this relation of phase current, line current, and power consumption in both the cases. So therefore, for the first case, we can simplify this delta connection by replacing with a star connection. So if you just replace with a star connection so that you can get easier analysis. So this will be R divided by 3. This is R divided by 3 because we know that in a star connected system, this per phase impedance will be 1/3 of the delta connected system. Now we can see here that line current IA. First we will see the line current. So the line current in first case, line current in first case will be line current in first will VA divided by R by 3. So so the line current in the first case will be, you can write VAN divided by R divided by 3. So you will get 3 VAN divided by R. And for this case, we will get line current as, in second case, line current will be, line current in second case, you will get VAN divided by R. Therefore, we can see that in the second case, it is getting 1 by 3 times of the previous value. So from the options, we can see that this option is going to correct. B option is going to correct because line currents will be 1/3 of previous value. Yes, it is getting one third. Now power consumption, power consumed we can find in first and second case. Power consumed will be, power consumed in first case will be, it is 3 root 3 times of VA a square, VAN a square divided by R divided by 3. So it is coming as 9 VAN a square. We are taking magnitude, so R 9 VN a square divided by R. And in the second case, power consumed will be, 3 times of VN a square divided by R. Therefore, the power consumption is also getting 1 by 3 times of the previous value. So D is the correct option. So B and D are the correct options. And for phase currents, how you can find? In this second case, we can see that line current is equal to phase current, so it will be same. And here in this case, first case, phase current will be root 3 1 by phase current will be 1 by root 3 times of line current, so it is getting reduced, so it will not correct. A is also not correct, and this is opposite to a power consumption, so both A and C are incorrect. Correct options are B and D. Now we will see the per phase analysis. Why, what is the per phase analysis? Per phase analysis is that thing that allows analysis of balanced three-phase system with the same effort as for the single-phase system. If you are given with balanced three-phase system, then you can apply there, you can make the equivalent single-phase systems and apply the single-phase concepts there in the balance for a balanced three-phase system. So this is called per phase analysis. And the balance three phase theorem says that for a balanced three phase system with all loads and sources are star connected and there is no mutual inductance between phases, then all neutrals are at the same potential and all phases are completely decoupled. That I said in the earlier. So all neutrals are same potential mean that if you suppose one node for source is n, a small n, and the other node is represented by big N at the load in, so it will be 0. Either they are neutral points are connected or not in a balanced three-phase system. This this voltage difference between node points is always 0. All phases are completely decoupled. That's why we can do per phase analysis. All system values are the same sequence as sources. The sequence order is we have been using here. Phase B lags phase A and phase C lags phase A, and we also called it a positive sequence. We will see this in Fortescue theorem, positive sequence, negative sequence, and zero sequence component. But whatever the phase sequence we have assumed, that is called positive sequence in a Fortescue theorem. So now we will see the procedure for per phase analysis. So how we will do the per phase analysis? For doing the per phase analysis, first you need to convert all delta load or sources to equivalent a star. And the second procedure, if you need to find the power, system power is apparent, that is apparent power, that will be 3 times of phase power, VAN IA a star. And if desired, phase B and phase C values can be determined by inspection. That is, they are leading or lagging by 120 degree. That is, they are having phase shift by 120 degree. So you just need to go with the one phase. Like if you have taken the, if you are doing the per phase analysis for a phase, then by inspection you can also find the values for phase B and phase C. And the fourth point is that, and fourth step is that if necessary, go back to original circuit to determine line to line values or internal delta values. If they, if in the question it is asked about the delta system, then you again need to go back to the original system after finding this, after doing the per phase analysis, and you can get the values. So first point is very very important. You have to convert all delta connected load sources to equivalent a star system, a star connection. And for that I have noted this point. This point is very important. For delta connected loads, it can be replaced by star connected loads by applying this expression: Z star is equal to Z delta divided by 3. And similarly for delta connected source, can be replaced by star connected source by applying this expression, that is V phase equal to V line divided by root 3 at the angle of 30 degree. So we will use this two expression for converting delta into star. So here I am also writing Z star is equal to Z delta divided by 3, and V phase, that if you are converting delta into star source, then V line divided by root 3 at the angle of 30 degree. And for delta it is given, V line voltage is given. So we are going to find this V phase. Is there any doubt? So now let us begin. Let us solve some problem. So actually I have solved some problems in the first session only based on the per phase analysis. So I have taken the general problems based on the per phase analysis. That is very very important. I have taken two or three general problems. They are not from GATE, but they are very basic problems. If you are able to solve these problems, then you comfortably solve these GATE problems also. Deepak, Ritesh, and Kangavel, Kangsabhai. So this is, so the question is that here, calculate the line currents in three wire a star system of figure given below. So I just want to tell you that you just approach the per phase analysis. Don't apply the KCL KVL in this three phase system. So for per phase analysis, what thing is the most important? What thing should be the given in the problem? First thing is that the three phase system balanced or unbalanced. For applying per phase analysis, the three phase system should be balanced or unbalanced. Anyone can tell?
Surveillance.
Yeah, okay, good. So three phase circuit should be balanced. So here we can see that all voltages magnitudes are equal and their phase displaced by 120 degree, and line impedances are also equal, and this load impedances are also equal. Per phase load impedances are also equal. Therefore we can write that the three phase circuit in shown figure is balanced. So now we can therefore we can replace it with its single phase equivalent circuit by per phase analysis. Single phase equivalent circuit. So let us take the, in per phase analysis, let us take this phase A only. Now we are going to make the single phase equivalent circuit for phase A. So it will look like this. So VAN and this is connected with line impedance. Per phase line impedance is given as 5 minus J2 ohm, and this is connected with load. Per phase load impedance is 10 plus J8 ohm, and this I've taken as source A and neutral point N for source, and this you can take capital A and N from the figure. So this is the per phase equivalent circuit. This is single phase equivalent circuit. By doing this, we can find easily the line current. So first we will find Z equivalent. Equivalent impedance will be series connection of 5 minus line impedance plus load impedance 10 plus J8. This will be 15 plus J6. That will come out as 16.155 at the angle of 21.8 degree. Therefore, line current, how much it will be? Line current IA. So we can say here IA line current. We need to find that only. Line current IA will be VAN divided by Z equivalent. So VN given as 110 at the angle of 0 degree volt. So 110 at the angle of 0 degree, 16.155 to 1.8 degree. So it will be coming as 6.81 at the angle of minus at the minus 21.8 degree ampere.
Sir,
Yes.
but load impedance, I think we have to divide by 3 to convert in
No, here
a per phase.
here all the impedances are given in per phase. 10 plus J, 10 plus, all the are in per phase only. And in the problem also, they always represent this whenever nothing is given, then you have to assume the per phase impedance only. If in the problem it is written like that, impedance is 5 line impedance is 5 minus J2 ohm, then you have to assume that it is given as per phase, not the equivalent, the summation of all the phases, right? So don't confuse that. All in the problem always impedance is given in per phase. Like for power, it is always given as three phase power, and for voltage, it is always given in line to line voltage. Right? Hello, Deepak.
Yes, sir.
Yeah, for voltage, in the problem, nothing mentioned what you have to assume, line voltage or phase voltage.
Line voltage.
Yeah, yeah. And for power, if is in the problem it is given that 400 watt power is given, then what you have to assume? It is you have to assume three phase power. And
Yes, sir.
if they wantedly write that this is single phase power, then you have to assume. Otherwise, nothing is mentioned. Then always remember, then for voltage it is line to line voltage. For power it is three phase power, and for this only impedance it is always given in per phase.
Yes, sir.
So similarly, we have done the per phase analysis for A phase. So we can write here how we can find the line currents IB and IC. So here the sequence matters. Like whatever the source voltages is given in that sequence, the currents will also be comes in that sequence only. You can write that since the source voltages are in ABC sequence, or you can also write are in a positive sequence. So in that sequence only the line current will come. So the line currents are also in a positive sequence. So IB will be is equal to IA magnitude but with lagging upon 20 degree. So it will be 6.81 minus 141.8 degree ampere, and IC will be lead the current line current IA by 120 degree. So it will be 6.81 98 98.2 degree ampere. Or if one wants to write is minus 240 terms, then you can also write 6.81 minus 261.8 degree ampere. So these are the answers for this problem. Now let us see the next problem. So any doubt in this problem? So moving forward to the next problem. So in this problem, a balanced ABC sequence star connected source with VAN 100 at the angle of 10 degree volt is connected to delta connected load 8 8 plus J4 ohm per phase as shown in the figure. Calculate the phase and line currents. So all of you try this problem. You have to find the phase and line current. And we know that for doing the per phase analysis, you need to convert delta into star. So we can approach both methods. Like in this problem, I want to show you that how you will find this using the conventional method and doing the per phase analysis. If you want to approach by conventional method, like we can take it at method 1 without assuming the per phase analysis. So we can say it as method 1. So if you apply the conventional method, just going through KCL and KVL in three phase system. So we are going to solve in that way, and after that we will solve using the per phase analysis. So here Z delta load impedance is given as 8 plus J4 ohm. So it is 8 point, if you write in phasor form, 8.944 at the angle of 26.56 ohm. And since phase voltage is given, VAN is given as 100 at the angle of 10 degree volt, then line voltage will be, therefore this is phase voltage. Therefore line voltage will be, we know that for line voltage it is root 3 times of phase voltage and leading by 30 degree. So it will be come out as 100 into root 3 10 degree plus 30 degree. So it will be 173.2 at the angle of 40 degree. So this volt, this is VAB. And this similar voltage VAB, this A and B, it is across this load also. So this is the similar to this same line to line voltage will come across the load also, VAB. Therefore, we can phase current will be what? Phase current you can see here. Phase current will be this one. Phase current will be this one. You need to find IAB, IBC, and ICA. So you need to find IAB, and we have found this VAB. And this is just as line to line voltage of source. That is VA minus VB. That is VAB we have found. So simply applying the phase current will be how much? So phase currents are IAB is equal to VAB divided by Z delta. So VAB we have found 173.2 at the angle of 40 degree divided by Z delta is 8.944 at the angle of 26.57 degree. That will come out as 19.36, 13.43 degree ampere. Similarly, this will be balanced in nature. So IBC you can write IAB at the angle of minus 120 degree. So it will be 19.36 at the angle of minus 106.57 ampere, and ICA will lead the IAB current by 120 degree. So it will be 19.36 at the angle of 133.43 ampere. So these are phase currents. Now you need to find this line currents IA, IB and IC. So how you will find this line current?
Root 3 time phase current.
And the angle,
Angle 30 degree.
lead or lag?
The leg.
Yes, correct.
But sir, I think this angle came from where?
Angle, this we have derived here. So here we can see that, see here we can see that this line current is lagging this phase current by 30 degree in delta connection.
Sir, this angle only come in the power system, not in machines or anywhere.
No, this is applicable for every place. Means, and some tutors also include this three phase system in network theory also. So this is applicable everywhere for three phase system. Whatever star and delta connection, it is applicable everywhere. Whatever this for a star connection, line voltage is leading by the phase voltage 30 degree and it is root 3 times, and for delta connection line currents are lead are of root 3 times magnitude of phase current and lagging by 30 degree. So it will be root 3 times of 19.36, 13.43 degree minus 30 degree. So it will be 33.53 at the angle of minus 16.57 degree ampere, and IB will be IA minus 120 degree. So it will be 33.53 at the angle of minus 136.57 degree ampere, and IC will be IA angle of 120 degree, that is 33.53 degree at the angle of 103.43 degree ampere. So here we have using the ABC phase sequence. Whatever the phase voltage in sequence, then this line currents will also in the same ABC sequence. So that's why we have taken by this phase displaced by 120 degree. So now we will apply the method second using the single phase analysis, per phase analysis. Method second using per phase analysis. Using per phase analysis. For per phase analysis, how you have to find? You have to convert delta load into a star, into convert it into a star load, convert into a star connected load. So how you will get Z star is equal to Z delta divided by 3. So it is delta connected load converted into a star connected load. So you can directly write the line current. Line current IA will be VAN divided by Z delta divided by 3. So one step we can also write Vn divided by Z star. So Vn is equal to Vn divided by Z delta divided by 3. So it will be 100 at the angle of 10 degree and 2.981 at the angle of 26.57 degree. So it will come out as 33.53, 33.53 at the angle of minus 16.57 degree ampere. And other line currents are obtained using ABC phase sequence. Similarly, you can write other line currents in the similar way. Other line currents are obtained using ABC phase sequence as above, that we have calculated in the previous slide. So we can see that applying per phase analysis, that make the simpler. So we can approach any way. So you can directly find the line current by converting the delta connected load into the star connected load, and you will get this line current that we are getting the similar value in the last slide. So now we are moving forward to the next problem, that is last problem for today's session. So here in this problem it is given that a balanced three-phase system with a line voltage of 300 volt supplies a balanced star connected load with 1200 watt at a leading power factor of 0.8. Find the line current and per phase load impedance. So for first part, let us make the equivalent circuit diagram. So let we have assumed that the phase let be assumed that let we assume that the phase with which we are working, like we have taken the phase A has a phase voltage with an angle of 0 degree, with an angle of 0 degree. So let us, that means I want to tell that whatever phase we have assumed, that we have taken that as reference, 300 divided by root 3 at the angle of 0 degree. And if you want to make the equivalent circuit diagram per phase diagram, then it will look like this one. Since this is leading load, power factor is leading, so we have represented by the capacitive load. So here this load is 400 watt at a leading power factor of 0.8, 0.8 power factor leading. And this V phase we have assumed taken as this one. Now we need to find this line current, right? And per phase load impedance. So line current, you can simply use this expression. Power, power in single phase is power in single phase is V phase line current. We are taking the magnitude only cos phi. So power is given as 400 watt. How? See here with 1200 watt at leading power. So load is given at 1200 watt. So per phase power will be 1200 divided by 3. So that's why we have taken 400 watt here. So in problem always whatever is given, that is 3 phase power. 300 divided by 3 IL cos phi is 0.8. So from here IL will come as 2.89 ampere. Now power factor is 0.8. So theta will come as cos inverse 0.8, that is 36.87 degree. That means if we have taken this phase voltage at the angle of 0 degree, then if we want to write in phasor form, then line current will lead this phase voltage by angle of 36.87 degree. So therefore this is the answer. And now this per phase load impedance, how we will calculate? It is simple. You have to divide the voltage with current. Per phase load impedance is per phase load impedance is Z is equal to V phase divided by IL. V phase is 300 at the divided by root 3 at the angle of 0 degree. IL is 2.89 at the angle of 36.87. So it will come as 47.95 minus J 35.96 ohm, and in phasor form it will be 60 at the angle of minus 36.87 degree ohm. So per phase load impedance will be 47.95 minus J 35.96. So this is R value and this is XC value, reactance value. And the second problem is that further a balanced 600-watt lighting load is added in parallel to the system. See here 600-watt lighting load. This is also given in three phase. So the per phase power will be 200 watt is added to the system. Determine the new line current. So for the next problem, it is given that we have the per phase circuit, per phase equivalent circuit. So per phase equivalent circuit is given like this, and other lighting load. So lightning load always works at unity power factor. It is resistive type of load. So and it is given as 200 watt. We can take it as I2 bar and it is given as I1 bar. So that does this I1 current will change after connecting this load 200 watt? Can anyone tell? Deepak,
Yes, sir.
this I1 current will change. Means we have calculated the I1 current here 2.89 at the angle of 36.86 ampere. So this I1 current will change after connecting the second load of 200 watt here. We can see this current will remain same as previous one or it will get change.
Sir, it will remain same because voltage is same and it is connected in parallel with voltage.
Yes, correct. Very good. So this is remains same because voltage is same. It is connected in parallel. Don't need to find I1. So I1 is remains same because the voltage across it has remained the same as the previous value. So I1 will remain same. I1 we have found 2.89 at the angle of 36.87 degree ampere. And for similarly we apply for lighting load as we have applied in previous case. For lighting load, per single phase will be single phase power is V phase. For lighting load we have assumed the I2 current cos phi is 1 because this is resistive load. So we can get single phase power is 200 watt. V phase is 300 divided by root 3 I2. I2 will come here 1.155 ampere. Now this is magnitude. Now if we want to write the magnitude, then what will be the angle of I2?
Sir, 0.
Yes, very good. So I2 will be 0. So the new line current will be summation of I1 and I2. The new line current is IL will be I1 plus I2. That you add up, you will get 3.87 at the angle of 26.6 degree ampere. This is the final answer. So that's all for today's session. And if anyone having doubt, they can ask Ritesh, Deepak, and Kangvel, Kangswai. And in the next session, we will see the inductance calculation. Yes, Deepak.
Sir, please share this PDF
Yes, I will share the PDF.
on YouTube channel.
Yeah, And for the
Yes.
video, you can refer this NPTEL Gate. You know how to get that?
Yes, sir.
Recording video is available on the NPTEL Gate portal.
Yes, sir.
Okay, Deepak. So happy Dasara to all of you, and we will meet after.
Happy Dasera, sir.
Thank you. We will on the next
Thank you, sir.
Saturday the same time.
Yes, sir. Bye.
Bye.